Next, we'll be looking at circuit performance. A common constraint when using a MOS device in a circuit is the power supply voltage. In our model, we'll be using a 2-volt power supply, assuming a 0.5 threshold voltage yielding a 1.5 voltage gate drive. These specifications are used to minimize high field effects and determine the limits of benefits of scaling device geometries. Being compared to a large power supply voltage, which will see the same deviation of transconductance observed on large device geometry. In our model, the device circuits can be separated into two different general classes, the gate capacitance limited circuits and the parasitic capacitance limited circuits. So to compare the two, an example of a gate capacitance limited circuit is a circuit whose load capacitance is dominated by a gate dielectric capacitance is a densely packed logic gate. And then an example of a circuit whose load capacitance is dominated by parasitic, other than gate dielectric capacitance, is a large bus line driver. In order to change the trend, or in order to change the circuit performance, we want to look at equation 16. In the case of gate capacitance circuits, and if we want to speed up the gate, if we want to speed up the circuit, we should definitely maximize the quantity of equation 16. If we want to speed up a parasitic capacitance limited circuit, we want to maximize the transconductance, which is the GM variable in the numerator of both sides of equation 16. So now we have our data from the model. We can see the graph on the right side, which puts the transconductance over device width versus the device length. As transconductance approaches a constant, the transconductance approaches constant as we decrease the channel length, and then this effect is caused by the channel carriers approaching velocity saturation at the source. And then also the transconductance increases with a reduction in gate dielectric thickness less than linearly. In order to sort of see this behavior, we need to normalize the data. So in order to normalize the previous data, we normalized by dielectric capacitance. We get the graph in figure 12. Still comparing transconductance width and device length. We observed that the magnitude of degradation decreases with decreasing the channel length. The carriers are approaching velocity saturation at the source. Under this condition, the effect of the mobility reduction with normal field on transconductance is reduced. So how does this overall affect circuit performance? With the insight of how scaling and changing the width or the length of the device and how it affects transconductance, we can look to improve circuit performance. For gate capacitance circuits, we do not want to reduce the dielectric thickness, but instead change the length, because the transconductance does not increase linearly with dielectric capacitance for practical device geometries. However, for the parasitic capacitor limited circuits, we want to reduce the dielectric distance. Although the increase in transconductance may be less than linear with dielectric capacitance, it remains significant for device geometries of practical interest, as demonstrated in figure 11 here. So what do we conclude from all of this? We conclude that this model predicts the saturation voltage decreases from the predicted by first order theory value as we decrease the dielectric thickness. Also, we predict that saturation voltage increases towards that first order theory value as we decrease dielectric thickness. We also saw the several observations concerning transconductance in prior slides. We also saw that in figures 11 and 12, the two graphs. And then for circuit performance, as mentioned previously, the changes in channel length and dielectric thickness can improve circuit performance based off of whether it's a gate capacitance limited circuit or a parasitic capacitance limited circuit. And thank you.